the peak value divided by square root 2 will give the RMS value of the voltage that is being provided by this transformer. So our peak inverse value of the voltage of this diode and the RMS value of this transformer is being decided. Now we'll move towards the second step of deciding the RMS value, the average value of the current of these diodes. If my load current supplied to this resistor is 5 ampere, and we consider that no voltage, no current is being synced to this capacitor, so we can say that this 5 ampere current is being supplied by these two branches. Considering that these elements, these diodes D1, D3, D4 and D2 are identical, and no kind of drop occurs in their way, in that case half of the current will come from this branch, 2.5 ampere, and half of the current will be supplied from this branch. So the average value, average current rating of the current of diode will be 2.5 ampere. So now consider this diagram in which voltage versus time has been plotted. This is the voltage profile that will be directly obtained in case of a full wave rectifier and no filtering is being used in our case. So when no filtering is being done, so the output voltage waveform will be like this. But if we consider that a capacitor is attached, is used as a filter just behind this resistor, in that case this capacitor will be will remove this ripple from our output, and we will try to achieve a nearly constant DC output waveform. The output will be oscillating or will keep on changing between the peak value plus the ripple on the positive side and the peak value minus ripple. That is like this is the V peak value, so delta V will be added and this value will come to this value to this point, and when this ripple will be negative minus 10 volt, in that case the average value of voltage will be reduced. So this is what the capacitor is trying to do. If this gives you the complete time period of this waveform corresponding to the input sinusoidal waveform, in which our the time period of our input signal was 20 millisecond, and now the frequency has doubled, so the time period from here to here will be 10 millisecond and 10 millisecond from here to here. So in talking in terms of the time period of the input signal, I can say that this time is the quarter of the time period of the input signal, that is T by 4. So the capacitor charges up to its peak value to this point, that is Vp plus delta V, and then it discharges from Vp plus delta V to the point Vp minus delta V, that is from 1010 volt to 990 volt, and then again it will charge up to its peak value, that is 1010 volt again, and then once again it will discharge from its peak value of 1010 volt to 990 volt. So the time period during which it will discharge from its peak value to the lower limit, that is 990 volt, is equal to the sum of T by 4 plus this time period T. Now keep this diagram in your mind, and on the basis of this diagram we will try to find the value of this capacitance, the different time periods associated, the T by 4 and so on. So let's start finding this. So the voltage, we know that the instantaneous value of the voltage at any point can be calculated as V is equal to Vm sine of omega t. Vm is 10 volt, that I am plugging over here, that is 10 volt, and sine of omega, instead of omega I will now plug in 2 pi f. But if you see here, I have added an additional 2 as well. This is because the output frequency is now 2 times. So instead of omega I will use 2 omega, that is sine of 2 omega t. This 2, it comes due to the fact that our output frequency is now twice the input frequency, and this is equal to 990. I want to I am considering the this at this point, that is 990 volt. So the equation of the voltage at this point is 1010 sine of 2 omega t is equal to 990. So basically what I am trying to do, I am trying to find the value of the time period when I will be at this point, that is 990 volt. This time period I have represented by t. So I will erase this mess from here so that we can get a clear picture of what I am trying to say. Okay, so once again listen to my point. What I am trying to do, I am trying to find this time t. And how can I find this time? By finding the equation, by writing the equation V is equal to Vm sine of 2 omega t. Why this 2? This 2 due to the factor that the output frequency is twice the frequency of the input signal, hence this 2 will come here. And now the second thing is, I want to calculate the time at which I will be at this point 990. So the time that will require to reach from this point to this can be calculated using this equation. V is equal to Vm sine of 2 omega t. So this is the V, the point at which I want to reach, that is 990 volt, and Vm is the maximum value, which is 1010 volt. So from this equation I can calculate the time corresponding to this equation. This time comes out to be 4.36 millisecond. So the time required to reach from 0 value to 990 volt is 4.36. And similarly, if I want to find the time period in which it will reach to its peak value of 1010 volt, in that case what will I do? I will modify the same equation, and instead of 990 I will now put 1010 volt, because I want to find the time during which I can reach from 0 to this point 1010. So if I put 1010 here and solve this equation, I will get 5 millisecond. And one important point is that see that this angle is not in degrees, this is in radian. So if you will do the calculations in degree, you will get a wrong answer. So you have to do the calculations in radian. And now we know that when will the diodes conduct. We have already discussed this in our previous lecture as well, that this diode will conduct only when this capacitor will reach to its this lower limit